In this video, we're going to talk about independence and mutually exclusive concepts in relationship to probabilities. We're also going to do a couple practice problems near the end. So, our main goal here is to define independence. Now, there's a mathematical definition of independence. The mathematical definition says, if you have the probability of A having chosen from B, and your answer is the probability of A, and if you have the probability of B having chosen from A, and that's the probability of B, and you have probability of A and B, and that just happens to be the probability of A times the probability of B, then you have independence. These are all features of independence. Now, you've just written that down and you just went, okay, that's nice. Can you explain that? And I could, I just don't feel it's probably the best way to explain independence. Although I will be circling back to these later on in some of the videos we're going to do. So we have the mathematical definition of independence, but I also want to talk about a more realistic and more tangible idea of independence. And very loosely, without writing this down, independence is actually asking you, did what you do affect the future? So is getting dressed and putting on your red shoes versus black shoes, like let's say you have just different color shoes, did that color of the shoe impact something in your future? And if the answer is no, the color of the shoe was completely irrelevant to the day and the world that was around me, then choosing that color of shoe was independent of other things that you're aware of. So that's what independence really means. Independence means, does one event affect the other? If one event occurs, does it change the other probability? So for example, let's circle back here a second. If choosing B first didn't affect the probability of A happening, and if choosing A didn't affect the probability of B happening, then A and B have to be independent. Because B did not affect the chances of A, and A did not affect the chances of B. So let's actually get down to that more tangible idea again. Independence. Does one event affect the other? All right, so two items are independent. So are independent. So I'll put I and D. So two events are independent if the knowledge of one event occurring does not affect, with an A, A-F-F-E-C-T, does not affect the other event. So two events are independent if the knowledge of one event occurring does not affect the other event. So now let's go to a casino mentally and think about all the games that you can play in the casino. And I'm going to pick 4 of them. I'm going to pick slot machines, roulette, blackjack, and the dice game called craps. So we can actually put all 4 of these in categories of independent versus dependent. So let's start off with roulette, which is a little marble that's spun around a wheel that is also spinning, and the marble will land in a section that's either black, red, or green. The roulette game is independent. The roulette game is independent because the marble does not affect future marble rolls. The marble has no memory. The marble doesn't enhance one section of the playfield or not. Let's think about blackjack. Blackjack has a shoe with many different decks in them, and there are all cards available. When a card is pulled out and put in front of you, no one else can get that card. That card is physically in front of you, and the deck is now smaller. blackjack is a very dependent game, and it's dependent because blackjack depends on what cards have been played already. People who decide to learn about card counting understand that the dependence of this game makes it available to counting techniques. I do not endorse nor suggest you try them, but it's the crux of why card counting became kind of a fascination event many years ago, with movies and books being written about it quite a bit. So let's think about the dice game, also known as craps. When you roll a pair of dice, do the dice remember what happened? Well, they don't. So dice games like craps is an independent game, because every time you roll, the die will not remember what to do for the future. So if you see someone roll a bunch and they don't roll 7 for a long time, and you can, add up the 2 dice to make 7, you're just watching an uncommon event, but it is still an independent event, even though the dice are doing something that's quite uncommon, which is not rolling a 7 in many, many turns. Those of you who play Settlers of Catan might realize that this feels like, if you feel like you're rolling 7s all the time, the dice aren't remembering what to do. The dice just roll what they roll. Now, slot machines. I really am going to be giving an opinion, but I feel it's pretty well grounded in some logic and science, that slot machines are dependent games. Slot machines are not random. And I'm sure that you can go back in time and find me concrete examples of slot machines that were made to pay out a certain amount, but the spinning of the wheels became random. Even though the chances of winning were small, it was still a completely random spin of the slot machine wheels. I kind of feel, and again, this is a hypothesis based on some science and some knowledge, that modern slot machines are programmed and by companies that are very versed in video games, such as Konami and Bally Midway. These are companies that understand the psychological impact of intermittent reinforcement. And I strongly suggest you dive into slot machine theory and slot machine psychology, and how it's a very easy and addictive system. And I don't mean to talk about any of these games to encourage gambling. I also enjoy blackjack a lot myself, but I just want to give you some heads up as to how these games are run or perceived, and definitely I encourage your future look. But a lot of times when we talk about replacement or without replacement, if you replace something every time, this helps with independence. D-E-N-C-E, excuse me. Now, the reason why we talk about this idea of helping with independence is, what if you did create a magical blackjack table where every time somebody picked a card, the card magically appeared back into the deck? Now, digital games can do this very easily, where you're given a card, but then it just kind of makes a deck of, the deck whole again every time you pick a card. But generally speaking, when we have a deck of cards and we're playing a game of cards, just as simple as, War, or as simple as Go Fish, these are played without replacement, and these are definitely not independent games. So, when you replace a card after it's been taken out of the deck, you're making the game independent, because now it's a new deck every time. But if you take cards out and keep them out, it's not independent. Now, mutually exclusive. We've got to basically debunk the idea that independent is mutually exclusive, and it's not. Independence talks about two separate events. Okay, so rolling the dice twice or picking 2 cards from a deck for your Texas Hold'em hold cards. The idea of mutually exclusivity is when the probability of A and the probability of 0 is impossible, which means that A and B share nothing or no elements. So this is when you're talking about 2 sets of a bigger set and they have nothing in common. So for example, if A represented all the even numbers in a deck of cards, so the evens, and B represented all the odd numbers in a deck of cards. Or if A represents a head on a coin and B represents tails on a coin. These are mutually exclusive events. They have no overlap. You can't have both at the same time. I can't have evens and odds unless I demand that, and that would just give me the whole set. But evens and odds don't naturally share an element. Heads and tails do not naturally share an element either. So what we're going to do in problems 21A through E is we're going to test this idea of mutually exclusive and independence by talking about flipping 2 fair coins or getting a heads or tails equally likely. So the tree diagram will always start with, and this is a little bit unlocking the last section of probability here that we're going to do until we hit maybe combinations and permutations and factorial in a later video. But this tree diagram is going to be you starting to flip, and you flip either a heads or a tails. That's your first flip. Now your second flip is going to be either a heads or a tails again. So what's happened here on this tree diagram, it shows you the 4 possibilities of your outcome space. So you could have flipped 2 coins in a row and gotten heads. So here's my sample space with the set notation, HH. Now, let's go down this path. Heads, tails. So heads, tails. This is another possibility. Flip a coin 4 times, you can get heads, 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 tails. What would the next 2 be? The next 2 results would be getting a tails, then a heads, and then getting 2 tails in a row. So your sample space has 4 elements in it. The elements of heads, 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 tails, tails, heads, tails, tails. So, let's look at F getting at most 1 tail. Let's find the set F, and let's find the probability of F. So, set F would be getting at most 1 tail. Now, a lot of you are going to pick this one right away, heads, tails, right? And you're also going to pick, that doesn't look nice. Let me make it nicer. I make this nice. So you're going to pick heads, tails very quickly. And then you're going to pick tails, heads, because that is getting at most 1 tail. Obviously, you wouldn't pick tails, tails, because that would be 2 tails. Some of you are going to miss this one, though. Heads, heads has, now it says, getting at most 1 tail. This had no tails. But this just made the requirement, I don't want more than 1 tail. And hey, heads, heads doesn't have more than 1 tail. So the probability of this set F would be 3 in the numerator, because there's 3 elements out of 4, or 75%. 0.75, 75%. Now let's get a pair. This is set G, which is getting a pair. And then let's find our set G, and then give us our probability of getting G. So set G will be heads, heads, and tails, tails. That's pretty easy to get. A lot of you figured that one out pretty great. Now the probability of G is going to be 2 out of 4, because we have 2 elements in this set, and we have 4 elements in set S. So our denominator is always our number of possibilities in this case. So this is going to be 0.5, stylistically 0.50 or 50%. Now, are F and G independent of each other? Which means that if I flip a coin to get this, this, and this, will that be independent from flipping coins and getting this or this? So will, excuse me, will the event of F affect G? Or will the event of G affect F? The answer is no. Doing any of these trials will not change the possibilities in the future. So are F and G independent? Yes, they're definitely independent. They're independent because flipping coins does not affect future coin flips. But are the F events and G events mutually exclusive? And the answer is no. They're definitely not mutually exclusive. And the reason why is because if we made a Venn diagram of F, which is heads, tails, tails, heads, and G, which is heads, heads, and tails, tails, excuse me, they would both have heads, heads in the middle. So no, because the probability of G and H, or sorry, G and, let me change that. The probability of F, oops, choose a different pen. Probability of F and G is not 0. They have something in common. See what they have here? They have that in common. And since they have something in common, so they have heads, heads as their as a shared possibility, these are not mutually exclusive events. So independence tests two different events at two different times, whereas mutual exclusivity checks to see is if one event is completely separate from another event, could they happen at the same time? And if they can happen at the same time, they are not mutually exclusive. For the final part of this video, we are going to take a look at a set of numbered cards. There are 3 red cards, numbered 1, 2, 3, and 5 blue cards that are numbered 1, 2, 3, 4, 5. This would be a great time to try these out before I get to them, but let's first together draw the sample set of cards. The red cards are numbered 1, 2, 3, so my first 3 elements are red 1, red 2, and red 3. My next 5 elements are the 5 blue cards. Blue 1, blue 2, blue 3, blue 4, and finally blue 5. So let's look at getting the probability of a red card. Pause the video if you want to try this. Probability of a red card is 3 out of 8. And that would be as a decimal 0.375 or 37.5%. Now let's look at the probability of an even card. Now even cards are 2, 2, and 4. So only 3 of these, 3 out of 8, which happens to be 0.375 or 37.5%. Now, going to go a little trickier here, right? We're going to do some conditional probability. Let's do the probability of choosing an even card having chosen a blue card. So I'm going to choose my denominator method here, where I'm going to list all my blue cards first. Blue 1, blue 2, blue 3, blue 4, and blue 5. So my denominator is 5. Now, let's choose an even card. Now, my only even cards are red 2, blue 2, and blue 4. Well, how many matches do we have? Well, we've got blue 4, and we have blue 2. So now the answer is 2/5. Now for those of you getting ahead of me here, you might actually just say, wow, so am I just choosing from blue all the evens that are in the blue? Great, yeah, you got it. You've leveled up. Because this is going to be 0.4 or 40%. So the probability of B choosing E is going to follow the same format here. So what I like to do is I like to write down my denominator first, which is writing down all of my even numbers, which is red 2, blue 2, and blue 4. So this means my denominator is going to be 3. Now you can see here where I can actually not write my numerator out because the probability of choosing a blue card from this set would just be 2. But in case you want to see this written out, here's blue 1, blue 2, blue 3, blue 4, and blue 5. How many pairs do we have? Or how many sets or matches? We got one match here and one match here. So this would be 2/3. There are 2 blue even numbered cards in the even numbered card set, which gives us a decimal of 0.6 repeating, or 0.667, or 66.7%. Now, it asks to list a pair of mutually exclusive events, and then name a pair of not mutually exclusive events. Well, getting a red or a blue is considered mutually exclusive because red and blue are mutually exclusive events. So reds, blues, mutually exclusive. There are no overlaps. Now, not mutually exclusive events would be choosing either a blue or an even. These are not mutually exclusive because blue and even actually have numbers in common, like the blue 2 and the blue 4. Now, how is each pull independent of the subsequent pull? And that's because what we did is we replaced each time. Trying to make this look a little nicer. Apologize for my bad handwriting. Replaced each time. So for each problem, we put all the cards back in together. Now, how could we change that? We could keep cards out. So as we pulled a card out, we could just keep it out so it couldn't be picked again. And that hopefully has done a little bit to clear up the misconception of independence and mutually exclusive events.